Greetings and welcome to the PLSQL channel, a series of video trainings on the Oracle PLSQL language. My name is Stephen Feuerstein, and I'm a PL/SQL developer just like you. This lesson is part of my series on writing maintainable code, code that you can write today and understand tomorrow, and 5 years from now have other people working on your code and still not have a nervous breakdown when they need to make changes. The topic of this lesson is write tiny chunks of code, one of my favorite pieces of advice for developers. Quick reminders. You can download all the code that I'll be using in this lesson and my other lessons from toadworld.com/sf, otherwise known as PL/SQL Obsession. Here's PL/SQL Obsession, lots of resources for PL/SQL developers. Click on the demo zip link to download and access all the code that I use to demonstrate techniques and also reusable code. Click on Training Seminars and Presentations to access underlying PowerPoints and PDFs to support my trainings. And of course, go exploring through all the rest of the features on the site. In addition, make sure you're comfortable with the material covered in the other lessons in this series, the importance of maintainability and along with that regression testing, the role of standards in maintainability, using key readability features of PLSQL, writing modular code with packages. So, write tiny chunks of code. So just as a heads up, I think if you follow this one piece of advice that I'll be giving you and elaborating on in great detail in this lesson, you can dramatically change the quality of code you write and the maintainability of that code. So what am I talking about here? Well, you've probably all heard of the term spaghetti code. And spaghetti code is pretty much the bane of a programmer's existence, the thing that puts us in a special kind of programmer's hell. It's impossible to understand and therefore debug or maintain code that has long, twisted executable sections. And that's really the hallmark of spaghetti code. Your programs just go on and on and on, page after page, hundreds, thousands of lines of code, impossible to figure out, impossible for even you to understand days after you wrote it. And it's the sort of thing we really, really want to avoid. And fortunately, it's actually quite easy to do that. It's easy to make spaghetti code a thing of the past for you. All you have to do is follow one simple to say piece of advice. Design your programs so that the executable sections have no more than 50 lines of code. In other words, keep your chunks of code, your executable sections, really, really small, so that at a single glance on a page or a screen, you can take in the entire logic at that level in your program. 50 lines of code, you might be saying to yourself, that's ridiculous. You write lots more lines of code than 50. You've got tens of thousands, hundreds of thousands of lines of code. Sure, of course, that's true. I do the same thing. I'm one of the back-end developers for Quest Code Tester for Oracle, and I'm responsible for maintaining something like 250,000 lines of code. You will definitely be writing lots of code. The question is, how will you organize all that code? Can you organize it in such a way to make it easier to manage? And it turns out that it's quite straightforward to organize that code, all of that code, so that it is transparent in meaning. In other words, anybody can look at your code and read it and understand what it means, what it's supposed to do, with a minimal need for comments. I don't know about you, but I don't like to have to write comments in my code. I'd much rather have the code tell its own story. And that's what this one piece of advice can do. Write tiny little chunks of code. And the key technique I want to talk to you about and apply are local or nested subprograms. So let's write some code. In terms of explaining this feature, rather than just show you what a local or nested subprogram is, there's not much to it. What I want to do is go through the process of implementing a complicated program to show you the steps that you should take and the kind of a discipline that you should approach it with. So let's suppose that my team is building a support application. Customers call with questions or problems about our products, and if we can't handle the call immediately, we put their call in the queue. Okay, so we've been building the application, the first version is in use, but now my manager comes to me and gives me a document that's 50 pages long and tells me, Stephen, you need to write a program that distributes the unhandled calls out to members of the support team. And it is a big, complicated program with lots and lots of documentation, but fortunately, there's an executive summary. And the executive summary says, while there are still unhandled calls in the queue. Assign them to the employees who are underutilized. They have fewer calls assigned to them than the average for the department. So if there's Joe and Sally in the team, Sally's got 10 calls, Joe's got 2 calls, Joe should get the next unhandled call added to his queue. So that's the basic idea. Now, one approach I could take is to start reading through the entire document, all 50 pages, and just start writing code. On page 1, I write code for that page. I flip to page 2, I write more code, and my programs get longer and longer and longer and longer, and I get lost. It's really easy to get lost in complex code and complex requirements. So what I want to do is avoid getting confused, avoid getting lost in all the details. So what I'm going to do is start with the executive summary. So the first step in this process of writing tiny chunks of code is to identify the highest level of expression of the algorithm of the program you need to write and translate it into code. So here's the first pass at my distribute calls procedure. I pass in the department ID. That's the department that has the support team members in it, to which I need to distribute the calls. And I'm going to more or less directly translate the executive summary. So, while there are still calls that are unhandled, for every employee in the department, if the current caseload for that employee is less than the average caseload for the department, then I'll assign the next open call. So I literally translate the contents of the executive summary into code. And what I do is come up with names of programs that will do the job for me. In other words, I hide the details behind a name. Now, do I know what it takes to determine if a call is unhandled? Not yet. I can read those 5 or 10 pages of documentation, but you know what? I don't even want to get into it yet. What I'm simply going to do is put a placeholder in my code saying, Stephen, you need to figure out how to determine if a call is unhandled. Stephen, you need to assign the next open call. And I just put off the details till later. Notice, I think this code is pretty readable. In other words, even though you're not a part of my team, you're not an expert in the domain of support applications, you should be able to read this code and make sense of it. So the subprogram names are used to tell the story. Okay, so let's assume that's true. You find this readable. We still have a problem though. These subprograms don't exist. I just made them up on the fly. Of course, to get this program to work, to put it into production, I have to implement the programs. So let's go through the process of analyzing these different subprograms, what they need to be, how they need to be written. So first of all, an explanation. My calls are unhandled function. It takes no arguments, and it returns true if there is still at least one unhandled call, false otherwise. Current caseload returns the number of calls assigned to that employee. So I have to pass in the employee ID, get back that person's caseload. Average caseload for department. That should return the average number of calls assigned to the employees in that department. And finally, assign the next open call. It assigns the employee to that call, making it handled as opposed to unhandled. So I've got a basic idea of what needs to happen. I've thought about what needs to go in, what needs to go out of each of my programs. Then let's think about some implementation. So the first thing I'm going to do is very simply add a stub into my main program, distribute calls. Add a stub definition for each one of my subprograms. Here's calls are handled, current caseload, average caseload for department, next open call. Let's take a look at this in actual code. So locmod, local modules, step by step. This file is in your demo zip. So here's my call manager package. I already had this program called show caseload. I've added a new program, distribute calls, while the calls are unhandled, etc., etc., etc. So here are all my different subprograms. They're not yet defined. So the next thing I'm going to do is define a subprogram, a function, procedure for each one of these subprograms. What that means at a minimum is that I can now get this program to compile, which validates the logic at this level of my subprogram. In other words, once I write these stubs, and notice they don't really do anything right now, but they do allow my code to compile. Once I get it to compile, I can say at this level of my program, I'm done. That captures the full logic of my distribute calls procedure. even though there's still more work to do at lower levels. But by taking this approach of hiding details behind names and expressing the logic, it's a lot harder for bugs to creep into my code because I'm simply repeating the requirements. And it's a lot harder for me to get confused and buried in hundreds and thousands of lines of code. So, I get my program to compile. Now, let's take a look at these program units here. This is a function defined inside another procedure, and a procedure defined inside another procedure. These are called local or nested subprograms. They can be called only from within the block in which they are defined. These can be reused, can be called and reused inside the current block, but nowhere else. They can reference variables that are defined in the parent block. So for example, if I define a variable here, like L department ID, then if I want to, I can reference that variable inside these local subprograms. In other words, this is a global for any of these subprograms. But in general, you should avoid doing this. This is also an example of referencing a global that's not passed through the parameter list. And in general, just as global variables in packages are dangerous to call or reference from other packages, if I have a global variable inside my procedure at this level, I'm better off passing it as a parameter than referencing it directly inside my local subprogram. But the fact is that this is defined at a higher level scope, so I can reference it. Only procedures and functions can be nested in this way. I can't have packages within packages. I can't put an object type inside a declaration section of my piece of code. I can't declare triggers. So this is functionality that's specific to procedures and functions, but boy is it a great feature. It allows me to hide details. It allows me to avoid repetition in my code. Really excellent feature, and it's the core of writing tiny chunks of code. And I suggest that you use this, nested subprograms, instead of nested blocks. In other words, I could write code like this. Instead of writing assign next open call, I can put it to declare. I can say declare my variables, begin, lots of code. Right inside my block of code, I can have other nested blocks. I recommend that you never use nested blocks like this. Instead, take that code out, put it behind a procedure name, define the procedure in that local block of code as a nested module, and then call it by name. That way, you can hide the details. It could be a very large nested block, and you don't want to get distracted from the main body of code and the main algorithm. This lets me see the entire algorithm at a glance. Okay, so I've defined my local subprograms. I get my program to compile, but it still doesn't do anything. So now I go down to the next level of implementation. I'm done at the executive summary, and I go down a level. I have to think about what the programs need to do. And then I ask myself, has somebody already done it? Did I already do it? The main thing is we want to avoid reinventing the wheel. And I realize as I look at this code, hey, just last week I wrote another function that's very similar to current caseload. It's now currently inside another procedure named show the caseload. I had a requirement for a report, show the caseload of an employee. I can't call it directly from distribute calls. It's a local private hidden program. So what I could do is say, oh, that's pretty good. I'm going to leave show caseload the way it is. Let's copy and paste it. Let's grab the code. Let's paste it into my new location. Let's make whatever changes are necessary. No, no, no. Don't do that. Instead, I should take the program show caseload and the core logic out of its current location and create a separate program that I can use in both places. So I previously just had show caseload, and that gets the caseload, calculates the caseload, and displays it. But I now need to call that, or I need to get the current caseload and distribute calls. So what I'm going to do is extract out the current caseload function ability, the ability to calculate the current caseload. And then I'll make it available in both of my subprograms. So current caseload used to be buried inside show caseload as inline logic. I take it out, I create it as a separate function, I call it from show caseload, I call it from distribute calls, and notice also that what will often happen as you do this, as you take logic that was inside one program and expose it for use in multiple programs, is that it will get more complicated. For example, I might need to add a parameter saying that I'm using it to show. In other words, I'm using it from show caseload, or I'm not using it from show caseload. Because if I'm using it from show caseload, maybe there's some additional functionality that's necessary or relevant to the display process.